Okay, so we are working through exercise 5C, which is about equivalent expressions. And what are our learning intentions? To know what it means for two expressions to be equivalent, and to be able to determine whether two expressions are equivalent using substitution. So let's go through some theory. So right here, we have a collection of pronumerals and numbers. So right here we have a collection of pronumerals and numbers which can be arranged into many different equivalent expressions. So what exactly does that mean? Well, as you can see here, I have 1, 2, 3, 4, 5, 6, 7 ones. And I have 1, 2, 3 A's. So I could write that as A plus A plus A. So I have 7 ones, which when you plus them all together is equal to 7. And I have 3 A's. So here is one way I could express this collection of pronumerals and numbers. Another way I could express it is that if I have 1, 2, 3 A's, I could say it's 3 times A, because 3 times A would be 3 A's. And remember, in algebra, we don't like that multiplication sign, so we could write it just like this, 3A. Another way I could write what is found in here is by going 7 plus 2A plus A, because 2A plus A will be 3A. So what we have right here are equivalent expressions. So it's a new word that we need to learn, equivalent. So it's basically different ways of saying the same thing, equivalent expressions. Equivalent expressions. Let's now read what we have down here. It says two expressions are called equivalent when they're always equal, regardless of what numbers are substituted for pronumerals. And we'll be going into that a bit later, substituting. For example, x plus 12 is equivalent to 12 plus x, because the order in which numbers are added is not important. 3k is equivalent to k plus k plus k, because multiplying by a whole number is the same as adding repeatedly. And that's what we saw here. A plus A plus A is the same as 3a. Okay, let's go through some examples now. So example 1 says, write 3 equivalent expressions for each of the following. So here we have 3u. Well, we know that 3u is the same as u plus u plus u. They're equivalent expressions. We could also say it's 2u plus u. 2u plus u is equal to 3u. If we really wanted to be smart, we could say that 4u minus u is equal to 3u as well. So right here are 3 equivalent expressions for 3u. Let's now move on to the next one, 4w plus 2. 4w plus 2. Okay, so we could say w plus w plus w plus w, because we've got 4 w's, and then you have to remember to plus that 2 on the end, that constant. So that's one equivalent expression. We could also say 2w plus 2w, because that's 4w plus 2. Or again, if we wanted to be smart, we could say 10w minus 6w plus 2, because 10w minus 6w will be 4w. All right, let's do the final one here, 3n plus 2m. Well, 3n, so that could be n plus n plus n, and then m plus m. Or we could say n plus n plus n and leave this as 2m. Or we could leave this as 3n and put m plus m here. So 3 equivalent expressions there. All right, example 2. For each of the following, choose a pair of equivalent expressions. So there is a pair of equivalent expressions here. F plus f, well, that's the same as 2f. 3f, well, that's just 3f. And immediately we know that 2f and 3f are not equivalent. They're just different. Here I've got 2f's and here I have 3f's. They're just different. What about 4f minus 2f? Well, 4f minus 2f is just 2f, because 4 minus 2 is 2. So what that means is this is equivalent to this, because they're the same. So this and this are equivalent. Okay, let's keep on moving over here. Here we have 2y plus y. Now 2y plus y will be 3y. And we have 2 plus 2y. Well, that can't be simplified in any way, so we're just going to write it like that. And then down here, this one, 2y plus 1. Well, this 2 means 2 times y plus 1, right? So we have 2 lots of y plus 1. So that's y plus 1 plus y plus 1. Y plus 1 plus y plus 1, well, I have a y here and a y here, which makes 2y. And I have a 1 here and a 1 here, which makes 2 because 1 plus 1 is 2. That makes sense. So I've got a y plus y, which is 2y, and a 1 and a 1, which is 2. And as you can see here, this is the same as this. 2 plus 2y is the same as 2y plus 2, because remember, the order in which you add things does not matter. And just like that, we're done. So this one and this one are equivalent. So we've found a pair of equivalent expressions there, and we've done so algebraically. We're going to learn more about it in our next lesson, but what we've really done here is we've collected like terms. We'll learn more about that later. But we've figured out which ones are equivalent through some algebra. Okay, let's now move on to example 3, which says, the rules of algebra are used to prove that two expressions are equivalent. So that's what we just saw above. We saw how we can use algebra to prove that two expressions are equivalent. But a table of values can be helpful to test whether expressions are likely to be equivalent. So now we're going to be showing you how we can use a table of values rather than algebra to do this. And this is what this exercise is all about. All right, so it says, which two of these expressions are equivalent? And we've been given 1, 2, 3 expressions here. We have to figure out which two of these are equivalent. What we're going to do is we're going to create a table of values like this. And then along the side here, we're going to put in our expressions. So 3x plus 4, 8 minus x, and then finally 2x plus 4 plus x. And now we're going to substitute in x equals 1, x equals 2, and x equals 3. So that means for this column right here, we're going to substitute in 1 into all the x positions there. So let's now give this a go. So if I put 1 into here, it's going to be 3 times 1 is 3, 3 plus 4 is 7. If I put 2 into my x position here, it's going to be 3 times 2 is 6, plus 4 is 10. If I put 3 into this, it's going to be 3 times 3 is 9, plus 4 is 13. Then we come down here and we're going to put 1 into this x position now. So it's going to be 8 minus 1, which is 7. So look, this looks promising. They're the same. Then I'm going to put 2 into this x position here. So I'm going to get 8 minus 2. Well, that's 6. So they're different now. So that means this and this, they're not equivalent because I'm getting different values out. And then finally, I'll put 3 in here, which will give me 5. And that's the nail in the coffin. These are definitely not equivalent. Well, we could have said that as soon as you get 1, that's not equivalent. It's definitely not. All right, let's come to our next one now. We're going to put x equals 1 into this. So that's going to be 2 plus 4 is 6, plus 1 is 7. Then I'm going to put 2 into this. So that's going to be 2 times 2 is 4, plus 4 is 8, plus 2 is 10. And then finally, if I put 3 into this, it's going to be, and I might even write this down so we're all on the same page, I'm putting 3 into it. So I'm doing that, plus 4 plus 3. 2 times 3 is 6, plus 4 plus 3. 6 plus 4 is 10, plus 3. My answer is going to be 13, so we put 13 there. So that's what we're doing. And now what we need to realize is, if I get my highlighter, this and this have given me the same outputs. So that means, what that means is that 3x plus 4 is equivalent to 2x plus 4 plus x, because I've gotten all the same values out when I substituted in values. So that means 3x plus 4 and 2x plus 4 plus x are equal for all values. So meaning when I substitute in any x value, I'm going to get the same output out. So they are equivalent. Perfect. So 3x plus 4, 2x plus 4 plus x are equal for all values, so they are equivalent. Perfect. Let's now move on to the next one, in which we're going to be doing the same thing. So let me just zoom out a little bit here. I'm going to be putting all of these into the left-hand side here. So 2a plus 6, 6a plus 2, 2a plus 3, and then 8a. Then I'll substitute in x equals 1, x equals 2, and x equals 3. And once you've done that, so let me just give you a kind of a demonstration for the first one. So you're going to go 2, and I'm going to be putting 1 into the a position. So 2, 1 plus 6, so it's going to be 2 plus 6, it's going to be equal to 8. So that means I'm going to get 8, 10, 12, 8, 14, 20, 8, 10, 12, 8, 16, 24. So you're going to spend your time filling out all of those until you get out all your answers. And then you're going to see which of these are equal. Well, it looks like this one is equal to this one. I'm getting all the same values out. So that means that 2a plus 6 and this one right here are equivalent expressions. So 2a plus 6 and 2a plus 3 are equivalent. Because they are equal for all values. Perfect. And we are done. So for this exercise, and this is exercise 5C, it does get you to make these tables for some of the questions. But normally, especially as you go further on in maths, and even in this topic, you're not going to be really proving equivalent expressions by making a table of values. It's important that you understand what's going on here and that equivalent expressions, regardless of what number you substitute in, you're going to get the same number out. But the major way that you figure out whether equations are equivalent is by doing so algebraically, which comes into like terms. So just to quickly talk about that now, 3x plus 4 and 2x plus 4 plus x. Well, here I have a 2x, here I have an x. So that means this one right here is 3x plus 4, which is the same thing as 3x plus 4. So doing a table of values kind of takes a lot longer than just simply doing it algebraically. You can just gather those like terms to figure it out. And so too with what we found here. And we'll talk about that more next lesson, but if we have 2a plus 6 and 2 brackets a plus 3, what this tells us is 2 times a plus 3, right? And that's the same thing as a plus 3 plus a plus 3. Well, I've got an a and an a, which is 2a, and a 3 and a 3, which is 6. 2a plus 6, which is what we have here. So even though in this lesson you need to know how to make this table of values, figuring out algebraically is far, far simpler. Okay, so with all that being said, we are finished this lesson. Hopefully you found it helpful, and I'll see you in the next lesson.